So welcome everybody. Thanks for joining us for this week's Geotalk. As you can see, we've changed tack slightly and go to groundwater. This is obviously a very important subject for all of us here in South Africa or Southern Africa. And we welcome to the Geotalk stage Seeke Mohuba, who is one of our own, a Witsy for life. Shirley, who's done all of her studying here at Wits. Yes, definitely. So Seeke studied her BSc and BSc honours here, and did an MSc in Hydrogeology and is now doing her PhD. And her MSc research focused on establishing environmental hydrogeological conditions at a potential nuclear power plant site. And she's going to talk about her current and her previous research. So Seeke, thank you for joining us and welcome to the Geotalk stage. So there we go, everything is ready for you. So I'll just put there and make sure that we aren't on mute this time, like last week.
Good afternoon, everyone. As Grant has already introduced me, my name is Seeke Mohuba, and I am currently a PhD student working with Prof. Tamiri. So on today's Geotalk, I'll be giving a presentation on a project I was involved in for my MSc, and it's titled Hydrogeological Characterization and Groundwater Vulnerability to Pollution Mapping of the Thuyspunt nuclear site. So like I said, I was working with Prof. Tamiri, and we were working in collaboration with the University of KwaZulu-Natal, and it was a project initiated and funded by the National Nuclear Regulator through its Center for Nuclear Science and Technology. So the Thuyspunt area, the study site, is located in the Eastern Cape Province. It's located about 120 kilometers from Port Elizabeth, and it's been identified as a potential site for the development of a nuclear power plant by Eskom. So we did this project because the nuclear regulator wanted to find out if the area is suitable to be used as a nuclear, as a site for the development of a nuclear power plant. So this is just the locality map of the study area. If you see here in the red, it's a demarcation of the study, the area that we focused on. And this area demarcated in black is the actual Thuyspunt nuclear site. So we extended our study outside of the actual nuclear site. And the area is largely groundwater dependent. So that's why we also came in, because there's a lot of different activities there, and they all are dependent on groundwater use, such as crop farming, such as dairy farming. It's actually the area is one of the biggest dairy producers in the country. And there are also a couple of nature reserves in the area. So it was very paramount to ensure that the environment is considered in case this site is actually, in case Eskom moves forward with developing a nuclear site in this area. So in terms of the geological setting of the area, it forms part of it's the eastern extent of the Table Mountain group, of the Cape Mountain range. And the main lithologies in the area, the Table Mountain group, it's composed of 5 geological formations, namely the Peninsula, Cederberg, Bavie and Skloof. The Peninsula, Cederberg, Bavie and Skloof, and Houdini formations. And it's a metasedimentary succession, and it's largely composed of quartzites, shales, and sandstones. And these pictures here, the top one is a picture of the Skouberg formation that dominates the coastal area. And then the bottom one is of the Peninsula formation. Overlying the Table Mountain group is the Bokkeval group, which is also part of the Cape supergroup. And in the area, it only has 2 geological formations that exist in the area, and it's limited to the North section portion of the study area, and it's mainly shales. And in the area, we have the Ceres subgroup and the Guido formation. And then the last geological unit in the area, which mainly dominates where the actual Thuyspunt site is the Cenozoic Alcohol Group deposits and mobile Ionian dune deposits. And these mobile dune deposits are currently active, and they form part of the Oyster Bay, St. Francis Bay Highland Bypass dune field, and it's fed by the proximal Oyster Bay and the Thames Bay beaches. And then this is just the field pictures that we took of the Bavian Screw Formation, so which forms part of the Table Mountain Group. So it's shales near the a lens cover for scale. And then this is the series subgroup of the Bokefeld group. And then we have the geopic for scale. And then the last one is the alien deposits, the mobile dunes that exist, the extensive mobile dunes that exist in the area. And the bottom picture is the indurated deposits of the Cenozoic Alcohol group. And the area has been subjected to extensive deformation and metamorphism, which is very crucial from a hydrogeological point of view, because it aided in enabling the rocks in the area to increase their water bearing capacity and thus deem them aquifers. So the area forms part of the Cape St. Francis anticline. And then if you look at the geological map here, here's the anticline. You can see the repetition in the geological units that represent the fault. So this is the Peninsula Formation with, sorry about that. The Cape St. Francis anticline. So here in this area where the actual Thuyspunt site is, it's dominated by the Cenozoic Alcohol group on surface, but at depth, that's when you encounter the rocks of the Table Mountain group. And along the coast, it may not be clear because of the markings of the boundary markings of the study area, but that's when you also get some of the rocks outcropping of the Table Mountain group as well. And the rocks, most of the rocks, particularly the Table Mountain groups, are subvertical orientation, which also plays an important role in aiding recharge for the aquifers and preventing seawater intrusion, which I'll explain further. So in terms of the hydrogeology of the area, we identified at least 3 types of aquifers. The first type was fractured unconfined aquifers, which were largely the TMG, quartzites, and sandstone. So these occur mainly along the coastal, sorry. Yeah. Okay. So we have the fractured unconfined aquifers, which are mainly the TMG, quartzites, and sandstones, and they're limited to the coastal sections of the study area. And we also have fractured confined aquifers, which are the same ones, the TMG aquifers, but the fracturing only comes into play at depth. And with the fractured confined aquifers, they also form an artesian system. And here's an image of a developed artesian borehole in the area. So as you can see, the artesian systems are highly, very acidic and highly characterized by highly acidic and iron-rich water. And the last type of aquifer, we have alluvial unconfined aquifers, which are the Alcoa group aquifers, and they are Ionian deposits, and these dominate the actual Thuyspunt site. So these are mainly the mobile dunes, so they form the alluvium unconfined aquifers. And underlying these alluvial unconfined aquifers are the fractured confined aquifers of the TMG. So based on results of an analysis using pumping tests and drilling data, we established the physical properties of the different aquifers. So in terms of the confined aquifers, the thickness varied between 18 and 126 meters, the transmissivity 0.359 to 44 meters per day, the hydraulic conductivity from 0.0089 to 1.5829, and the groundwater level was varied from 4.43 to 28.97, which is a great variation because the variation in groundwater level speaks to, again, the suitability of the site to be deemed safe for the development of a nuclear power plant. And in terms of the unconfined aquifers, there was also a great variation in the thickness, the transmissivity, and the hydraulic conductivity. Pardon me, I said the groundwater level. It varied, it was a minimum of 3.5. So these are only the ones that we were able to actually measure the depth to groundwater, but there were other boreholes that we weren't able to measure because of inaccessibility. So in terms of the recharge of the area, it was estimated to vary from 4 to 72 millimeters per year, and this was based on the water table fluctuation method, which essentially measures the changes in water level, in groundwater level in each aquifer, and then those changes, any rise in the water level, so any increase in the groundwater level is assumed to represent recharge. So that's how we estimated recharge, because other methods that existed, because of the conditions in the area, such as the chloride estimation method, we couldn't really use because there was already chlorine present in the system. So the estimations were going to be an overestimation of the actual recharge. So there are a variety of springs in the area, namely context springs. So with the context springs, they mainly occur, they dominate the study area, and then they occur where there's a change in, so sorry, if I could just move to the next slide. So here with a schematic representation of how a context spring works. So you have rain that falls, or you have a surface water body, and then when the surface water infiltrates, it infiltrates into the mobile dunes, then into the indurated dunes. Then at greater depth, there's the quartzite, which has a great difference, which greatly differs from the overlying dunes in terms of its porosity, its transmissivity. So because of the physical barrier, the water cannot percolate into the quartzite. So because it's at the contact, it's permeable. It's impermeable, I meant to say. So a spring will form along the contact. So that's how we get context springs. And like I said, they dominate the study area. We also have depression springs. And we also have coastal springs, which dominate the coastal section of the study area. And we also have fracture control springs. As I already mentioned, the area is highly fractured. So there are a lot of fracture springs that we encountered in the area. And in terms of groundwater circulation, the groundwater circulation is very regional, so is recharge, although we did identify areas of point recharge. And in terms of the point recharge regions, so this is a groundwater flow map indicating how groundwater moves. So the arrows indicate the direction of groundwater movement. So at this point where the arrows, at this point where the arrows are diverging, it represents a point recharge area. So it's a point recharge area that we identified. And when you look at the arrows, the general flow direction of the groundwater is towards the ocean. Moving on to the hydrogeochemistry of the area. So the calcium magnesium bicarbonate hydrophases was the most common water type, meaning that in most of the groundwater that we analyzed, the dominant major ions were calcium, magnesium, and bicarbonate. And this is largely attributed to the calcareous cement for the quartzites, as well as for the indurated dunes. And there was also a lot of hydrochemical evolution noted in the groundwater. This is a Durov diagram. So this arrow here, this arrow here, it's the Durov plot. It represents the migration, the evolution of water. So it evolves from calcium, magnesium, bicarbonate water, which is deemed fresh, to more saline water. So this blue arrow here represents the evolution of groundwater. And this evolution was noted along the groundwater flow path. So in general, the groundwater in the area, in the more inland areas, it's more calcium, magnesium, bicarbonate rich, but with more converging groundwater flow paths, it evolves to sodium chloride rich water. And in terms of the hydrogeochemistry, what largely controls the water chemistry in the area is water rock interactions. and as well as mixing of different waters. So with water rock interactions, it's mainly dissolution, hence calcium, magnesium bicarbonate is the dominant hydrophacy. And there's also mixing of different waters. And these are the samples that plot in cube number 5. So this represents waters that whose hydrochemistry is controlled by the mixing of different waters. So moving on to the stable isotopes, we use stable isotopes to identify if there are any links between the different water bodies. So if there are any links between the different aquifers, between the aquifers and the springs, between the wetlands and the aquifers. So with the stable isotopes, you see that all the groundwater samples, which are represented by the maroon triangles, are all depleted, heavily depleted in stable isotopes of oxygen and deuterium. So what this means when they plot in this area is that the moisture source of the groundwater, of the rain that eventually recharged the aquifers, originated from a higher altitude moisture source, and that recharge also occurred during colder seasons. Because with a high altitude recharge moisture source, the heavier isotopes rain out. So when you get to higher altitudes, the moisture source will be depleted. Will be depleted in the heavy isotopes. Hence, we see a lot of depletion in the stable isotopes of the groundwater. Also, based on these results, we noted that there was a hydraulic link between most springs and aquifers, the springs being the green circles, so the groundwater being the maroon diamonds. So if there's a lot of isotopic similarities, and this makes sense because springs are a superficial manifestation of groundwater. So we learned that most of the springs are actually connected to the aquifers. And there's also some connection between the wetlands and the boreholes, meaning that the wetlands do help recharge some of the aquifers during periods of high rainfall, and during dry periods, the groundwater contributes water to the wetlands, thus sustaining the wetlands during dry periods. So because here there is no hydraulic link between the ocean, there's no isotopic similarities between the ocean samples, which are these here, and the borehole samples. So we're able to deduce that there is no hydraulic link between the ocean water and aquifers, meaning that there is no ingress of seawater into the sample aquifers. So there is no seawater. There is no seawater pollution in the sampled aquifers. So moving on to radioisotopes. So we use these to determine the resident times of water, which you can term the age of the groundwater. So how long the groundwater has been in the subsurface. So based on tritium, the ages varied from 5.92 to 49 years. And then this variation signifies that there's a difference in the recharge times. So with the 5.92 residence time of the groundwater, it implies that the earliest, the youngest recharge in the area. So the latest recharge that took place in the sample aquifers was 6 years ago. And then with carbon-14, we also use it to estimate the residence time of the aquifers, but we do these for older water, so water that has been in the subsurface for a longer period of time, for hundreds to thousands of years. And with these, we found that it varied from 430 to 1,000 years old, and this was found in the deep circulating aquifers. So in the artesian systems, which are located at great depth. So with the age, with the high residence time, it shows that there is a hydraulic disconnection of these aquifers, between these aquifers and the current rainfall that are occurring, the current recharge, because all the water in these aquifers is hundreds of years old. And what this also means in terms of the difference in the tritium ages and the carbon-14 ages shows that there is a hydraulic disconnection between the different aquifers. So the upper aquifers not all the aquifers, I meant to say, necessarily feed the lower aquifers. Hence, there's a difference in the resident times. So this map here is just a special distribution of tritium in the area. And then in general, you can see that tritium generally decreases towards the ocean. So you see the more blue, the blue shades represent lower tritium units. So with lower tritium ages, it indicates a longer residence time in the subsurface. So because once tritium enters the subsurface, it undergoes radioactive decay. So the lower the unit is, it implies that the tritium has been in the subsurface for a significant amount of time. And with this trend, it's not surprising because the recharge areas, as I indicated, are regional. So recharge occurs further inland. So as the water travels towards the ocean, where its discharge point, the tritium undergoes radioactive decay, resulting in lower tritium values. So in terms of the background, chemical and radiation characteristics of the water, rocks, and samples, we also did this so that we can establish the background values in case the nuclear power plant starts being operational. So they will use these results to benchmark any changes. So they will be used as a reference material. So in general, the Skaalberg Formation quartzite, which is of the TMG and forms most of the aquifers, the productive aquifers in the area, as well as the series subgroup shales, contain the highest activities of radionuclides, such as uranium-238, uranium-235, 234, radium, thorium, and lead-210, as well as high activities of metals such as thorium, lead, and uranium. And this was attributed to the mineralogy of the rocks. And the soil as well, especially the soil at the actual Thuyspunt site, had high readings of lead, thorium, and uranium. And this was attributed to contributions from the series subgroup shales and the sandstones in the area. And in terms of the exposure dose rate, so we also measured the radioactivity in the area to estimate how much the exposure dose rate essentially measures how much radiation your body will be subjected to when you're exposed to these rocks. So the exposure dose rate was highest in the series subgroup shales. And with the series subgroup shales, it is worth noting that these shales are quarried. So there's a quarry in the area, and these shales are quarried and used for construction. So it was very alarming to see that they have high exposure dose rates and they're extensively used for construction purposes. Sorry. So this is just a representation of the conceptual model of the area. So here we have a cross-section of the geology in the area. So this is the peninsular formation of the TMG, and you can see the fold in the repetition in the geology in this direction and in that direction. So essentially what this shows is that the annual rainfall that the area receives when it falls onto the ground, some of it percolates, infiltrates into the surface, and then it will fall into the mobile, it will infiltrate into the mobile dunes of the area, and then these will percolate further. Not all the water that infiltrates will form part of recharge. Some of it gets discharged as interflow, so it never actually makes it into the aquifer, and some of it dries out due to evaporation. And then these red lines here represent the confined system. So the confined aquifer systems that I mentioned earlier, where we have the artesian boreholes. So they come from these areas. And then the shales of the Cederberg group, of the Cederberg formation, I meant to say, form the confining units to the peninsular formation aquifers, confined aquifers. So we also did a groundwater vulnerability to pollution mapping. So what this essentially does is it assesses if the area, the groundwater in the area, the aquifers, are vulnerable to any pollution. So we first check the intrinsic vulnerability of the aquifers, meaning the natural vulnerability of the aquifers in the absence of any sufficient anthropogenic activities. So it's a 7 parameter based test. So it works in GIS. So what it essentially does, it considers 7 parameters: the depth to the water table, which is the groundwater level, the recharge in the area, the aquifer. So the aquifer media, meaning the type of material that constitutes the aquifer. So for example, if it's quartzite, or if it's the sandstone or the dunes, so they'll have different physical properties. So we also have to consider that. The soil media, which mainly forms the top layers of the unconfined aquifers. The topography, which has an implication for whether there will be recharge or runoff. So if any rainfall that falls will either recharge, will infiltrate, that's potentially contributing to recharge, or if it will run off. The impact of the vadis zone. So the vadis zone is the portion of the geology that exists above the groundwater level, as well as the hydraulic conductivity of the aquifers. So what happens is these maps are then overlaid. So we have a map for each parameter. We create a special map for each parameter, and then we overlay them in ArcGIS, and then the net result will be the intrinsic vulnerability of the aquifers. So the first map indicates the intrinsic vulnerability of the aquifers. So with this, we see that majority of the Thuyspunt site, this area, is deemed as highly vulnerable, intrinsically highly vulnerable to pollution. And this is related to the shallow groundwater depth in terms of the depth to groundwater table, the recharge in this section, because the material is largely the dunes, which are highly porous. So when there's rainfall, it infiltrates better than on these areas on the outside of the study area where you have quartzite, which have less porosity. The topography in the area in terms of this is also very steep. So it's gentle. So then it allows for water that any rainfall that forms to actually reside on surface, that increasing the chances of percolation and infiltration. And we also did a specific vulnerability test. So with this one, you check the vulnerability of the aquifers with respect to a specific activity. So in this case, because they want to construct a nuclear power plant, so we checked the aquifers potential vulnerability with relative to nuclear activity. So we created a hypothetical nuclear power plant here. And then the results show that even with the nuclear activity, the area is still highly vulnerable. The Thuyspunt site is actually highly vulnerable to pollution. But note that high vulnerability to pollution doesn't necessarily mean that the area will be polluted. It just means that if there are no preventative measures and mitigative measures, the aquifers will eventually get polluted. But just because it's highly vulnerable, if there are mitigative measures that are put in place, then the aquifers, the groundwater, can still be protected and there won't be any pollution. So in conclusion, we identified at least 3 types of aquifers, and with these aquifers, they have variable physical properties. The area has a complex geology, which was crucial in aiding groundwater circulation as well as recharge, and also the complex geology enabled the lithologies that are normally in their normal state wouldn't usually have the capacity to bear water. So massive rocks such as quartzite, which are less porous, wouldn't usually be good aquifers, but because of the deformation and the deformation and the folding and the fracturing, they've become highly protective aquifers. We also noted that the strong link between majority of the aquifers and surface water bodies, specifically the springs and wetlands, as well as a hydraulic connection between the different aquifers. So the hydrogeochemistry of the area is mainly controlled by water-rock interactions, specifically mineral dissolution, as well as the mixing of different groundwaters due to the different flow flow lines of the different groundwater systems. And regional recharge in the area dominates over local recharge, and groundwater generally undergoes regional circulation as opposed to localized circulation. And in the Skarberg Formation, which is of the TMG group as well as the Seeke subgroup, contain the highest radionuclides and radiation levels, and this in turn affects the quality of the groundwater, because these two formations constitute the productive aquifers of the area. And the footprint area of the Thuyspunt site, the aquifers in the footprint area are intrinsically highly vulnerable to pollution, both intrinsically as well as specific vulnerability to the nuclear activity. Thank you very much.
Fantastic, Seeke. Thank you so much. That was great. You can stand right here.
Okay.
Don't move it. Don't move it. All right. So we have some time for questions. That was a really interesting talk. This is based on your MSc, right?
Yes.
That's fantastic. We can't wait to hear about your PhD. Right. So any questions from the audience? I have a few, but let's first see if there's anyone in the audience with some questions. Or in the online audience, anyone in the online audience with a question? Bring up the chat. While we're waiting for questions, then I'll ask my question. So I have two questions. The first is about the safe levels of radionuclides in drinking water in general. In the area you looked at, are those levels of radionuclides at a safe level, or are they actually currently higher than what is considered safe drinking water?
In the groundwater?
Yeah, in the groundwater around the site.
In most of the aquifers, they're generally safe, with the exception of groundwater that is hosted in the Skarberg Formation quartzite. So because there are already high levels of radionuclides in the actual rock, and there's high water rock interaction, so the levels in those ones are actually higher than the drinking water standards.
Okay. So does that, my follow-up question is, does that make it a good place to put a nuclear site, or a bad place to put a nuclear power plant?
For me, it's an ideal site to put a nuclear power plant, because with the what do you call it? Although it's vulnerable, like the area itself is vulnerable, it doesn't, like I said, doesn't necessarily mean there'll be pollution. And one thing that helps is that the direction of groundwater flow is towards the ocean, and the fact that there isn't any interaction with there's no ingress of seawater into the aquifers. So maybe in terms, if you're thinking of if they're using the groundwater, the seawater to cool, and then that gets polluted, what if then it pollutes the aquifers? But because there is the way the area is structurally, the way the rocks are oriented, it doesn't allow any seawater to ingress into the aquifers. And also because the groundwater, the recharge is regional in the area. So the recharge at the actual site is very limited. So most of the surface water that you encounter there, very little of it actually goes into the groundwater. The recharge areas are further inland. So then what happens at the site has minimal effect on.
Great. Any other questions?
So, I wanted to ask also about the pollution of the water from the sea. I saw some of your points with some few points on the seaside, where you say this, the water is more saline, the fact that it's affected by the seawater. They said there's no any ingress of water. And what about those few points? Please go back to slide.
A table.
The way you had different points and then some on the side. So does it mean that so there's no any
Oh, okay. The stable isotopes.
Yeah.
Yeah,
This
it's one for those coins.
Oh, these ones.
Yeah.
No, so there's no, if you note all the groundwater samples, so all the borehole samples plot on this side. So it's the maroon diamonds. And then the seawater samples are these two samples here. So all these samples are depleted in stable isotopes. So they're significantly different from the seawater samples. So the seawater samples are enriched in stable isotopes, and these ones are highly depleted. So yeah, and the sodium and chlorine rich water that comes from the geology of the area. So it's not because of it's not the groundwater. There's minimal impact of the ocean on the actual quality of the groundwater.
Just on that, I mean, could some of those squares, which are wetland, are they not pointing towards
The wetland.
ocean and
No, so with the wetlands, so what happens is when, isn't it it's a surface water body. So when it's subjected to evaporation. So here's another thing I failed to mention. Thank you for that. These lines, it's a local meteoric water line and global meteoric water line. So we use that when we interpret. So when points plot below the global meteoric water lines, as do these two squares, it indicates that the groundwater was subjected to evaporation. So with these ones, the enrichment in stable isotopes is not because of the ocean, but rather because they've been subjected to evaporation. So when evaporation happens, the first, as the water evaporates, the lighter isotopes get evaporated first. So the resulting water will be enriched in the heavier ones. So that's why these ones plot them.
What about those ones in the bottom left square? So
What?
you've got all your red points and there's some wetland squares.
Oh, these ones.
Yeah.
These-
Are they not drawing lines towards ocean and number?
No, you don't. So these ones are different. So these ones are more, these ones are more controlled by the groundwater. So these are the wetlands that are actually sustained by groundwater during dry periods. So there's a lot of groundwater contribution to the wetlands. So hence they plot this, they isotopically similar to the groundwater.
Okay, and then a few more questions online. Let's go to the top here. Right, this is a slightly long question. So if an aquifer gets polluted, it'll be hard to control it because even if pollutants are removed, the polluted aquifer is still intact and more infiltration will keep on stripping the agents from the aquifer. What are some of the measures that are in place to mitigate this or will be in place if there was a power plant? Can you answer that?
Yeah. Well, I definitely agree. Once an aquifer is polluted, yes, it will be difficult. It's almost impossible to reverse the damage, which is why it was important for the nuclear regulator to have this study done so they know how vulnerable the aquifers are to potential pollution. So what we did, we just gave them the existing conditions that are of the area, and then I guess their next step would be to ESCOM to tell them, okay, we see there's a high vulnerability potential for pollution in the area. So what measures will you have in place to ensure that the aquifers are protected?
Great. Okay, then one or two more questions. This is from Brandon Yulton. Does potassium in the shale contribute to the radioactivity?
Yeah, it does. It does. It certainly
That's the
does.
source of the radioactivity.
Yes, it certainly does.
Okay, and then
So with just to add on to that one,
Yeah.
so it does also to the exposure dose rate that I was talking about. Yeah, it does contribute to it. Yes,
Right. And then a question from Adem Ali. Just curious, did you get a chance to measure radioactive levels in the coastal waters near discharge sites? Do you think this environment is also highly vulnerable to radioactive pollution?
Yes, we did. Some of the like these springs that we measured, springs. So these springs. Yes. So he's saying the radioactive levels in the water. Yes, we did using the handheld gamma spectrometer, and we also collected water samples, and we submitted them to the lab to get the activities of each different radioisotope. And then with these ones, with the coastal ones, because most of the discharge points, the water is from the radionuclide rich Stolberg quartzites. The radiation was, the reactivity was high.
Okay, and I think there's one last question from the audience who generated a lot of interest in. Okay, so this one is from Sipo. I don't have much experience with respect to this method. I'm aware it uses the water level to estimate the recharge, but considering that your study area has stakeholders that use predominantly groundwater, how is the estimate affected, and do you have seasonal data?
All right. How do, sorry, Mr. Gorgeous?
The WTF method. Yes.
I'm worried uses, it's such a long question. Sorry, let me just read it.
Yeah, go for it. You read it.
I'm sorry, water table fluctuation.
There we go.
Yes, water table fluctuation. That is predominantly how is it affected? So with the WTF method, right? So obviously, because people do extract water from these aquifers, they do pump. So with it, how it works is you will have a period where you're measuring so you have water loggers in the bowls. So you have a period where the groundwater is being measured. So like I said, because it works on the assumption that any increase in groundwater level is a result of recharge, water recharging the aquifer. So you focus on, so there will be periods of decline and increase. So you focus on the areas where there is an increase. So when you pump, yes, there will be a decrease in the groundwater level, but if there is a recharge that is resulting in a net increase in the groundwater level, you focus on those, because the basis of the method is that the increase of groundwater in groundwater level is assumed to be a result of recharge. So,
yeah, but according to Sipo's question, your answer must be that water table fluctuation method has been applied in monitoring boreholes, not in pumping boreholes.
All right. Okay, thank you for that.
If pumping, then groundwater
it will be declined, yes.
So these were applied in ESCOM controlled monitoring boreholes. Nobody is using them. So that's for testing monitoring.
Okay.
Yes, and
great.
Also, do you have any seasonal hydrochemistry? No, we don't have seasonal hydrochemistry data. Yes, the hydrochemistry data we don't have, but water levels, we do have continuous data of that, just not the hydrochemistry data.
Super. I see there's a few more messages, but I think we'll leave it there for now. So Seeke, thank you so much. Anyone who wants to ask any more questions of Seeke is welcome to stay behind for some virtual networking at the end.
Right.
But let me just remind you of next week's talk. It's by Kenneth Rapitsoa, and he'll be talking with Musa Manzi on innovative mineral exploration solutions and case studies from the Bushveld complex. So please come along and join us for that. And Seeke, thank you very much once again for a really interesting talk.
Oh, I'm sorry, if we published 2 papers on this research. So if you are interested in knowing more about that, you can find them online.
Yeah, you can check out Seeke's papers online. Thanks everyone for joining us, and we'll see you next week, same time, same place.
Thank you.
Cheers.